There we are. Those who saw me yesterday, welcome back. Those who see me for the first time, hello. For a second day in a row, I have the job to keep you awake after lunch. Not me alone, there are some other people in other rooms, so thank you for choosing this one. And I will talk to you about a project that I ported from C to C#. And who knows C? Show of hands. Quite a lot of you, cool. So you know what pointers are, right? Do you know you can do pointers in C# as well? But you don't want to, because it's unsafe. And this is, I could have go for the easy route and say, hey, I'm just going to use pointers everywhere, port to C as close to C as possible in C#, and done. But I didn't want to. I wanted to use all of the safety rules that we have in C#, the garbage collection and everything. So this is that story. Now, the original story, or the original title of this session is actually Doom#, porting a C project to C#. Why? Well, because in the summertime, I sometimes have way too much time on my hands, and I get these crazy ideas like, let's build a Game Boy emulator, or let's build a Nintendo emulator. And in the summer of, I think it was 2022, I got the idea, the Doom source code is open source. I might as well port it to C#. I wasn't the first one, but I wanted to do a fresh one myself. Now, if you port any C project to C#, it's probably going to be because you might have a very old library that you want to reuse, and then for some reason it's maybe easier to just port it to C#, so you can easily package it in a NuGet package, bring it into your project, yada, yada, yada. Then you can take whatever I'm telling you today with you as tips. It also is a very good thing to have a lot of knowledge about the source that you're porting, or the library, or the project that you're porting. Now, unfortunately, I was not involved in creating Doom, the game, because when id Software created this game in 1992, I was only 10 years old. So that would have been too early for me to already work on this project. But however, there's a lot of information about this. Well, first of all, it's open source. Secondly, the source code is pretty well structured. It's pretty easy to read. And there's a lot of books available about this source code as well. So if you want to learn all about Doom, there are documentaries, books, everything. I am Wesley, by the way. I work as a coding architect at Xebia in Belgium. I love coffee. I love beer even more. So I'm glad to be here. And well, as I already said, I have some crazy side projects as well. Before I dive into the code, let's show you a little bit about the progress that I made in the project. So I started quite late in August, and a few days after, the first thing I had to do is like read the materials of Doom, like everything that they store, like the graphics. And then the first thing I wanted to do is just show the title screen. And this was the title screen. That worked great. You also see on the right-hand side the console output that you get when you launch Doom. And then a few days later, I started working on the rendering mechanism. So 8 days later, this is the demo that starts playing if you don't play yourself, because I did not have any input handling yet, but this was the demo that started playing. So rendering mostly works, but you see there's still a blank space at the bottom, and that's where normally you see the status as a player. So I started working on the status bar, and a day later I had that working. He looks very mad, but he was being hit, probably. And then I started adding the input handling. So I started working on how to transform keyboard input into player action, and this is what I'd like to call the pogo stick incident. So you start the game, you fix the screen size because there were still some graphical glitches, and then I start running. At first I look around, and then I hit the forward key to start walking. But I walk really weird. I started jumping like on a pogo stick. So I had to, of course, fix that problem. And now I have to find out how to go to the next slide. There we go. A few days later, I had those rendering and movement bugs fixed, and I could already also interact with items and areas. So I could pick up the armor, walk around, shoot things, and so on. And then by September, I got the game 80% finished. So I could play the game, I could even finish a level, and then everything was almost implemented. What did I not implement? The cheats. Sorry, you can't cheat in my version yet. All right. Now, when I wanted to port this, I said I didn't want to use the unsafe keyword, but what is the unsafe keyword? Now, when you write C# code, most of it's verifiably safe, which means that the compiler knows enough to know whatever you're doing here is going to be safe to run in the .NET world. That doesn't mean that unsafe code really is unsafe code. It just means that it can't be verified that it's safe. So whenever you want to do unsafe in your projects, you first have to mark your project as this can contain unsafe code. Just adding the unsafe keyword does not work. You get a compiler error, you have to check that box first. And then whenever you need to go unsafe, you mark your code as this piece is unsafe. Just like you have the using construct, this is an unsafe context. And in that, you can do that for a code block, you can do that for a method or for an entire type. And that gives you then the capabilities to start using pointers so that you can immediately interact with memory addresses rather than having the garbage collector do stuff for you. Now, on the right side, you see some example code. This is code coming from the Microsoft documentation page. And let's see what this does. So first of all, we have to say this is our unsafe part of the code. We just have an int array with some items in there. And then we're going to immediately access that array. So first of all, we want to have the address of the first element and store that in the pointer p. And we have to use fixed. Because if we don't use fixed, the garbage collector might move that array around in memory without us knowing it. Because that's how the garbage collector works. It optimizes your memory for you so that you don't have to deal with these things. But if you want to have a direct access pointer, you need to pin that pointer in memory, that array in memory, so that the garbage collector says, okay, I'm not touching that thing unless you stop using a reference to that thing. Next, we create a copy of that pointer. So we want to have a pointer 2 to the same address. And then we use the star to dereference the pointer, reading the value from that address, and then outputting that to the console, in this case, the number 10. Then we increase the address by 1 position, not 1 number. That's a huge difference. This is, you're moving the pointer with the size of 1 int. C# is smart enough to do that. So now your P2 is pointing to 20, and your original pointer P is still pointing to 10. If you then do a console write line of P, you're still writing 10, and then you do the div reference plus equals 1, which means you're increasing the element, so not the address in this case. Yeah, okay. So again, unsafe does not mean that your code is not safe, but there's just no way that .NET can know that it's safe or not. Which is a fancy way of saying, here be dragons. Now, the reason why most people would use the unsafe method and use pointers is performance. Most people think if you address everything directly, it will be more performant. Well, that still depends on your coding skills. I do have a case in this source code where direct referencing is being used. That's on the Android version of my port for a specific reason. But most cases, if you take that example again and you translate it from the unsafe version into the safe standard C# version that we know and love, what would be the performance difference in this case? Let's benchmark this. But before I benchmark this, let's also look at the intermediate language. Who has never seen intermediate language in C#? All of you have seen intermediate language? Cool. most people never go that deep into the code. Is this readable? More or less? Let me make it a little bit more big. Better. So this is the same code, the unsafe one. So we have that address of number 10, and then we store that in a pointer, which in the most recent versions of C# is a native int these days. And on the right side, you can see, okay, that means we're going to load a 0. Sorry, this is already, it tries to help me, but this is actually already here. So it loads the number 0, that's this one. Then it's loading the address of the element at position 0 from an array, which is this thing. And then it's storing that in the first position in my stack, which is putting on the stack. Then I can load it from the stack again and put it into this one. And that's what happens here. That's that conversion. I'm duplicating whatever's on the stack, which is this one. And then I'm going to dereference that address, which is load indirect from address. Indirect meaning it's going to use that address and reading from the address immediately. And then it's calling system console write line. Nothing really interesting happens for the rest of this, but that's how pointers work, indirect and addresses. Now the interesting part is, this is the safe code. So pretty much the same thing. The address is now my index, 0. I'm going to store that index again. But then the interesting part, if I look here, if I immediately go to my array and using that index say, hey, I want this item at index position 0 to now become 11 instead of 10, look what I'm using. This is not me writing pointers, but behind the scenes, the C# compiler compiles down into an indirect addressing method as well. Because the compiler in C# is smart enough to say, hey, these things can go blazingly fast if I just immediately go to that address space and manipulate the data in there, rather than getting the data, doing +1, and storing it in the array. So it's already doing some stuff that we deem to be unsafe for you, even if you're not using unsafe. Now looking at the benchmark, I ran it in .NET 6, 7, and 8. I did not run it in .NET 9 yet, but I'm pretty sure that it's going to be probably the same result. There are next to no differences if you use the unsafe versus safe in this particular case. So using unsafe or using pointers does not necessarily mean faster code. As you can see, the differences are, these are microseconds, so I would say negligible. And the only interesting part is that since .NET 8, we have a lot less memory allocated. Well, I say a lot less. This is still in the bytes region, but you can see that some optimizations were made here. Of course, again, not always the case. Because when I finished creating my port, I messaged a friend. He created the Android version using Maui. And when he started to run that on his phone, he has a pretty fast Android phone. It was slow as hell, the game. Because we had to populate the graphics, and then we used indexed graphics, which means that you have a table of color references, and then you have a table of colors. And to update all of these data on Android was so slow that it didn't work. So there we had to use unsafe to immediately update the stored arrays, and then it was way faster. So there is a difference in some cases. Cool. Memory management. What do I mean with memory management? Well, of course, if you know C and C++, you have all the memory management available to you. You can call malloc, or you can allocate a block of memory, you can reallocate stuff on the fly, and then you have to free it, because otherwise you have a memory leak. And then if you do C++, you have the options to do new and delete, and then use them in a bit more easy way. So for example, if you take a very simple thing where you have a name array, you can just pre-allocate your name to have 100 characters, or you can say, I don't know the length of the name up front, so let's allocate enough size of characters so that we have a name2 which is just long enough. And then we can, for example, copy test into that name2. Please don't use that code. Use the ones that are safe and have like the strn copy, so that you know how much characters you're going to copy, or the maximum length of your array. But you can also do weird stuff in C and C++. It's not because I have a pointer of characters that I can't suddenly decide to say, I'm going to address this as if it were integers or something completely different. So I can immediately go to that address of my test string and just say, I want to have that position interpreted as an integer value. And that works just fine. Now, this is still a very safe example. Nothing would prevent me to say, hey, I have this structure in C, and now I want to go to that address within my string and interpret that data as that structure. It perfectly works. As long as your memory space is available to your application, you don't get an exception thrown by Windows. Of course, you have to free your stuff at the end again. And then in C++, creating those classes or structs and newing them up is a lot easier, because now you can just say, hey, I want a new person, instead of having to calculate the size of a person and saying malloc size of whatever, and then delete instead of free. Now, the reason I'm telling you this is because in the source code of Doom, they also use memory management. Remember, this game was released in 1992, and the PCs back then, they typically don't have a lot of memory to work with. I think the original game required about 4 megabytes of RAM. You can see here, this is actually already the updated version of the source code for Doom 2, and they required 6 megabytes, so you can see that constant on the top. And they used malloc to allocate a block of memory, and they stored that as a simple byte array. And then they used something like zones to organize that memory into memory zones, and then they could put whatever they wanted into that zone. Yeah, byte array, I already said that. So whenever you then interpreted, for example, you loaded a level contains vertices where your walls begin and end. They load that structure of data inside that chunk of bytes, and then they say, okay, I need now enough room to store, let's say, 100 vertices, so that's the num vertexes, times the size of one vertex, and then store that in one of those memory blocks that you have, and then they tag it with a certain indicator, in this case it's level, to say, okay, whenever the level's finished, free all the level data, so that this is their memory management. Now, I don't have to do this. I could have implemented the same level of memory management, but I have a more modern language, so I could use just my garbage collector to clean this up for me. Also because what's the average number of memory that the average PC has these days? I hope it's 8 gigs. Most of you probably have 16 or 32, so I'm not going to bother with having to allocate 6 megabytes of memory. So I just used arrays. Very easy. You just have your new vertex of num vertices, you load them in, and you're done. Easy, right? Nothing fancy here. Now, you could have also said, but Wesley, what if you don't still know how long your list must be of data? couldn't you just have used list of t instead? Yes, I could. But I wanted to keep the code close to the original, and the original used arrays. But let's see, if we use list of t, what would have been the difference between a list of t and a simple array? So in this case, I've run a few tests. For example, I used a pre-allocated array. So I know I'm going to have this many items. I pre-allocate that size and then do my tests. I do the same with a list. So if you do a list and you know in front that you will always have 100 items, you can say new list 100, and then you have 100 items of storage pre-allocated. Then I used the simple standard dynamically resizing list. So I do new list, and then just use list.add, and it will resize itself. And then I did the same with arrays, but 3 times. The first time, I'm using the double sequence resized array method, which is actually what list of t is implementing as well. Every time you add an item, the list grows by 2, and then 4, and then 8, and then 16. You can also just say very naively, the chunked version, I'm just gonna, whenever you add something to the array, and you don't have enough space anymore, just add 10 more spaces. I just chose that number by rolling 2 dice and then 10. Or I can aggressively resize it, which means every time you add a new item, just grow by 1, which is very poor performance, I can already tell you. So this time I only show you the results in .NET 8. I have all of the results in my slide deck, and you can get the slide deck afterwards. But you can see of course, the list version, both pre-allocated and dynamically resized, they perform pretty darn well. So the time that it took to run the benchmark is only slightly higher than a pre-allocated array. Only the difference is that the memory usage went up when you use the dynamically resized version, because you do have to resize your thing, and you're actually over-provisioning your array. That's the only downside. Of course, it should not be a surprise if you use the same algorithm as list uses and you do it directly in arrays, you end up with more or less the same performance. It's just slightly better because you have less overhead than the list does. And then we have my own poor versions. The aggressive one, growing every time, also means you have to copy your data every time, which is why that almost takes 100 times more than the original time. And it also allocates almost 2 megabytes of data rather than only 4 kilobytes. And if I do my easy resize and say every time you run out of items, add 10 more slots, that is faster, but still almost 18 microseconds rather than just 7 or 8. And also, you allocate 215 Ks instead of just 4. You might think these are rookie numbers. You have 16 gigabytes of memory available. This is fine. But at this moment, I'm actually working for a customer that uses embedded hardware where the resources are limited. So these limits might come into play at some point in your career, where you have to really think about using as little allocations rather, and as little of memory as available. But I could have used lists and saved myself a ton of headaches. But you will also see, whenever you look at, for example, the Kestrel source code, you will see a lot of arrays being used, because when this code hits a lot, then arrays are still the way to go. Let's move on to binary data. Why? Well, the Doom source code, it loads in one big file when it starts. And that file is the WAD file. WAD stands for Where's All the Data. That file is like a directory containing a table of contents, and in that table of contents you will find at this position in the file are all the textures that you need. At this position are all the level data. And then inside the level data, it points to another part in the file where you can find the vertices, the scripts that you need to run, and so on and so on. Those are called the lumps. So whenever you read that file, this is plain C. You open the file handle to that WAD file name. You specify that you only need read access to that file, and it's a binary file, so you need to add these two tags. And then when you can open that handle, then you can start reading from that handle. In this case, you're trying to read the what info structure, which is why you have to say this is the number of bytes I'm going to read, the size of that structure, and you're putting it in that address of header. This looks quite readable to me as a C# developer, because if I look at the same code in C#, this is how you would typically do that. So you open a file stream, and I'm not using the using statement because I'm actually keeping a reference to that file before someone asks. I'm opening that file, just like in the C code. I'm using read access, and I'm not sharing this file because I'm an egocentric person. I don't want anyone else playing Doom while I'll play Doom, basically. And then I open a binary reader, so I can read contents from that stream. I know that the data inside is using ASCII mode, and I'm going to, whenever I close that binary reader, I will close the underlying file stream as well. And then I can start reading from that file, just like before. So if I load that what info header thing, I can then get some bytes. For example, I know that the first 4 characters should be either IWAD or PWAD. So I read 4 bytes, interpret that as an ASCII string, and that's my identification part. And then I read the next thing is an int32 value, and the next thing is an int32 value as well. This is a bit different than reading the structure in C and then immediately parsing it into the header. Why? Because this is easier to code for me. I could have used a struct, I could have used Marshall of whatever, but this is way easier and it's as fast as whatever I need to do. Now, let's say that you want to use file lumps. What's a file lump? It is the structure, for example, that says this is a texture, and you can find that texture at that position, and that texture is this many bytes. But what's the size of that structure? So, how many bytes is a character? Is this Unicode? Is this ASCII? Is this something else that we don't know yet? How many bytes is an int in our system? In the .NET world, it might be that many bytes. It's 4 bytes for us, but an int has not always been 4 bytes. On some systems, it's only 2 bytes long. So we have to know how long this is, and we have to really be careful with those sizes if we start reading stuff, especially if you convert a code base from an old system to our current devices. So don't make assumptions what the size is of a structure. Read the documentation of the original file data if you can. Luckily for this game, there's an entire wiki section to know what sizes these should be. In this case, 16 bytes. But that's not the only thing you need to think about when reading binary data. You also need to think about NDNS. For example, if we take that value 4A, 3B, 2C, and 1D, you can represent that in big endian mode, which means most significant byte goes first, and your number value is actually represented as 4A, 3B, 2C, and 1D. Typically used by the Motorola 68000, which is very old, Sun Spark, which is also old, and mainframes, which are also very old. Now, what we mostly use is little endian, which is where you flip everything around. So your number is now stored as 1D, 2C, 3B, and 4A. As you can see, the Intel x86 platform uses this, which is basically everything that we use. Also used by the very old 6502 processor or the DevConf. Now, the funny thing is, when I created these slides, I learned something new. There's also something called middle endian, used by the PDP-11. Luckily, only the PDP-11, because that's a mix of both. And that's the worst part of it. It can be one of two options. It can be that they swap the half of your values around, so they keep the order 2C, 1D, for example, but it comes first and then 4A, 3B. Or it could be that they keep the original words order, but then flip around the bytes in that word. So you get 3B, 4A, and 1D, 2C. If you ever come across a system like this, run. Again, I was lucky to find some documentation that said everything that you will see in the source code is little endian, but there was one port of Doom. I don't know if you can play it here, but they have an Atari Jaguar downstairs. The port of Doom on the Jaguar was using big endian. So they had to, because the Atari Jaguar was big endian, they actually had to reverse everything in the WAT file as well. Cool. Now, there's one kind of pointer which I do like, and that's a function pointer or reference pointer. Why? Well, I was implementing that status bar, and then I had a little bit of a problem, because in the Doom source code, they implement this as widgets. So everything that you see here, like the ammo and the health, that's a widget. Actually, already pretty well-structured code. So they used object-oriented way to saying, this is the status bar, and this part will represent the ammo, and the ammo knows enough to know what value to put in there. For example, if you look at the health widget, they give it a dedicated X and Y position on the screen, and then the talnum is an array of all the font indexes that they can show the 0 and the 1 and the 2. But then they reference the player's health immediately. They can because it's C. So they have an object for the player has a health property, and here they say, I'm giving you the address of that health variable, so whenever you need to update yourself, you can read the current health of the player. That's something that we cannot do in C# unless you use Unsafe. And then you have to pin the player object in memory, because otherwise your garbage collector will move the player memory object around all the time. So this is not really something you can do. Now, if I give this piece of code to someone who's just out of school, they learned C#, and I say, I need some way to access the player's health without using pointers, so you have to somehow give it by reference. Aha! Reference, I know this. There is a way that you can say, I give you, dear function, something by reference, which means that you have always the latest version available to you. Correct? But you're not storing the reference here. The only thing that you're doing here is, at the moment that you run this function, I give you the value, and if I manage to update that value will be going back to the original caller, but you're not giving the address. So this does not work for you in this case. Okay, then what about if I wrap it? I create a reference of int, and then I store whatever I need to store in that class, which is an instance, and then I can access it. Yeah, that would work. But that also means that wherever I need to interact with the player's health, I need to know that it's now a reference of int, because everywhere that you have this health, you now have it wrapped into a reference of int instead. It's not the best solution that you can implement in this case. There is a third solution that we use all the time, a func. Just give it a func of int. Instead of referencing the memory address, just give it a way to get to that memory address. In this case, whenever I create my widget, I say, hey, here's a way that you can access the player's health whenever you need to, which is basically the same as in C. Rather than using a memory address, in this case, it just knows by a function to do this. So if I show the code of that same widget in C#, this is my version. So again, you have that X and Y position, that array of digits that you can display, and then, hey, whenever you need the player's health, here's how you can get it. And that works just fine. And again, this is the C# version. That's the C version. Not a lot of difference. I think the biggest difference is the way you format the code. But this is not the only place where I had to deal with special pointers. There's also something called thinkers and map objects. So a thinker is something that can react in a level. For example, it can be a door that you can open or close. Some doors open automatically. Some doors open when you go over a certain line in the level. Some doors can even be opened by enemies. There are also ceilings that can start coming down on you when you enter a room, and then you have to quickly move out of the room before they crush you. Or floors that become a staircase. A map object, that's a special thinker. You, the player, you are a map object. Every enemy is also a map object. And every map object gets the map object thinker method assigned to them. So this function will actually, whenever you update the state of the game, it knows how many map objects are in play. And for every map object, you get the first reaction as a player, you get the highest priority. Your map object function will run first. And then every other map object in the game will have their chance to update. For example, an enemy heard you, so now it decides to start moving towards you with one step at a time. Or he sees you, he's close enough, he will take a shot at you. And the way that works is, well, first of all, it is a linked list, a doubly linked list. So the structure of a thinker has a reference to the previous one and the next one in the list. And then it has an action that it can take, which is the action F of T structure. And the action F is a union, which means it can be either the action FV, action FP1, or action FP2. And the difference is, action FV is void, it doesn't do anything, so, well, it does do something, but this action does not have any parameters, and it does not return anything. And then P1 has one parameter, and P2 has two parameters. So that's already a problem for me, because whenever I see action F, it can be actually three kinds of actions. I don't know. At runtime, it might be one of three options. Second problem, the ones that have a parameter, I don't know what parameters these are. You can see void star. That means it can be anything. If you see void star in C and C++, that means something. Figure it out. Of course, in this case, if you give a method to that action f of p, the method knows what void star is going to be. It's, for example, it's going to be a door or a player. But you don't know this in front. If you just see this, you don't know. So, yeah, I should have used these. What I came up with is I used an action, because void, func returns something, action returns nothing. And then I wrapped those three options, having no parameters, having one or two, into an action params record. See, I'm a very modern developer, I already use records. And then I looked at the source code of Doom and found out that whenever they added a parameter, it was either a map object, or it was the player, which is a special map object, or it was a player sprite, or it was a thinker. And then and every time when they used these parameters, luckily for me, they were only using specific combinations. So whenever something is null, I knew exactly what the intention was. So, yes, of course, I should have known my slides by now. So in this case, we have the method that operates a vertical door. And in this case, it's very simple. This method only uses the thinker parameter of that action params. So I can easily say, okay, if my action params.thinker is not a door, because I can immediately cast that door into a variable, then I return. I never come into that section, but it's a safe way to code this. And then I can start looking at the direction that the door is supposed to go and then take action to say, okay, you have to go up or you have to go down. And that is how I made all of this work. So to summarize what I've seen, most important thing, unsafe code isn't necessarily unsafe, but it's also not necessarily more performant than you might think. It is quite easy to translate C into C#. C++ is going to be more difficult, especially if you have someone who likes to use multiple inheritance. Try to do that in C#. It won't work. And method pointers can be a bit more challenging, but you should be able to get around using delegates or actions of funcs. So this is basically how I managed to do everything. Now, this is the moment where you can ask a question. You can also already grab the slide deck if you want to. So, do you have any questions? How much time does it take? That's the most obvious question. Well, actually, not as much time as you'd think. I took about a month to get it working in 80% of the 80% state. There are a few things that don't work, like the secret level. You can't go into the secret level. If you manage to get to the end, you can't finish because I did not finish the interaction with the boss mob. You can't cheat. You can't type text. You don't get any text updates when you pick something up. There's like you picked up a health file and something. There's no network connection available. And what else? I did add sound and music support, but I added that like a year later when I tried to do so for the Android port as well. But most of the things were ready in a month. No. No, I did not. But I can say, when I wrote the Game Boy emulator, someone, not me, created custom Game Boy ROMs to test every functionality of an emulator. So there's a Game Boy ROM that allows you to test if you implemented the microcode of the CPU correctly, if you implemented the correct interrupts timings, or the screen, it's like an area where you have to go blank mode and then you draw. So in that case, I did use the test ROMs to test my emulator as well. But in this case, because id Software didn't want to write unit tests, I also didn't bother writing unit tests for this code.